Welcome to the next episode of Thermodynamics. Today you are going to learn about molecular kinetic theory of gases. Molecular kinetic theory of gases describes a gas as a matter which consists of molecules or atoms which constantly move in a closed space such as a closed container where they collide with walls of the container and thus consequently pressure appears. Motion of such a big number of particles can be considered statistically. In this observation, we neglect the dimensions of particles and their repulsions and attractions, so that the only thing we can observe are the perfectly elastic collisions. Let's take a case of a gas in a cubic container. A gas particles move in three main directions. First, draw this cubic container. This gas is enclosed within. So cube, and within this cubic container we have some gas particles. Much more than this, but here are gas particles, and they move in one of three main directions, so-called degrees of freedom. First is up down, so this direction. They can go up and down, up or down. Then left right, and finally this one, which is to us, away from us. So in this direction, to us or away from us. So these are so-called degrees of freedom. The force a gas particle of mass m and velocity v1 acts on the container. So we have a gas particle. Let's take one gas particle which has mass of m and goes at velocity equal to v1, and it bumps into a container wall. And this force is F equal to ma according to the second Newton's law of motion. Since acceleration is proportion of speed change in a time interval, we get that F equal to ma equal to m times acceleration is change of velocity over change of time, so time interval. From this we get that F times delta t is equal to m times delta v, thus J is equal to P, where J is impulse and P is momentum. So this relation is known as impulse-momentum theorem. When a gas particle goes towards a wall, it goes at velocity of v1 equal to v. So the speed of this velocity v1 is equal to v, and when it collides with the wall, it repels with the velocity v2. So when it collides and it repels the opposite way back with velocity v2, and this v2 is same as v1, and v2 velocity is minus v, so has magnitude of minus v, and here we have this minus because we know that the collision is of opposite direction, but here we have this v, so the same magnitude v as v1 has v2, because we know that collision has to be perfectly elastic for an ideal gas. Having that in mind, we can calculate speed change. So delta v is v1 minus v2 or v2 minus v1, and we have that it is 2v. And now the distance a gas particle travels from one wall of the container to the opposite one, which is equal to 2 lengths of a cube of edge A. So let's name each of these edges, its length, width and depth with A. So this distance is equal back and forth equal to 2 lengths of a cube of edge A, one edge length traveled forth and one edge length traveled back in same direction, so distance is 2a. And then time interval delta t is equal to proportion of this distance 2a divided by speed v. So delta t is 2a over v. Now take the impulse momentum formula, so this one in the upper right corner, and then put this matching delta t and delta v into it, and then express force F from it to get that F of particle. So first let's do this. So F times delta t is 2a over v, is equal to m times delta v is 2v, and from this we get that F of a particle is mv squared over a. However, it is force, so this F particle is force of only one gas particle. So we have to get pressure on volts of all gas particles which go in one of these three directions, up, down, left, right, or to us, away from us. This is third of all gas particles if we assume equal number, and third of all gas particles goes into each of three directions, where big N is total number of the gas particles. So total force in one direction, this, or this, is equal to N third times this mv, this force of a particle, which is mv squared over a. From this force we can get pressure P as proportion of this force F, and surface S, which is surface of a cube face. So surface S of one cube face is a times a squared. We have square as cube face, a squared. So P is pressure, proportion of force, and surface this force is acting on. And this force, as we've said, is equal to n thirds times mv squared over a, and all of this over surface, which is a squared, and it is equal to n third times mv squared over a cubed. Furthermore, we have a cube, which is actually the cube's volume, so a times a times a is cube volume, which can be denoted with big V. So this one is big V, cube's volume, and mv squared over 2 can be written as kinetic energy, Ek. Here we don't have 2, but we can multiply it by 2 and then get the final expression. And finally, after some expression transformations, we can get that PV is equal to 2/3 NAK. So product of pressure and volume is 2/3 of number of gas particles enclosed in this container times their kinetic energy Ek. If we write the number of gas particles big N as the product of amount of the substance small n, and Avogadro's constant Na, big Na, which is expression derived from the formula for amount of substance, we can equate the expression with an ideal gas law, PV equal to nRT. We get formula for average particles kinetic energy. So kinetic energy, but average, of a particle is 3/2 kT. We get using all of these formulas I mentioned, where this K is so-called Boltzmann constant, and it is actually proportion of R over Na. So proportion, Boltzmann constant, is proportion of the ideal gas constant and Avogadro's constant. Since this is average kinetic energy, Ek particle average, so this bar meaning average, we can conclude that internal energy, that of all of the gases, or all of n gas particles of the ideal gas, is n times this kinetic energy. So here we have two formulas. First is for the gas internal energy, U, which is equal to EK1, so kinetic energy of the first particle, but average one, we cannot say the exact, plus average kinetic energy of the second particle, plus, all the way to average kinetic energy of the last gas particle of this ideal gas enclosed in this cubic container. And we get that it is actually n times, so the total number of gas particles being n, times average kinetic energy of a particle is 3/2 kT. And if we apply this ideal gas equation, we get that it is 3/2 nRT. Actually, we get this by applying this formula for amount of substance, which is that amount of substance is proportion of number of entities and Avogadro's constant Na. And from this formula, 3/2 nRT, which is internal energy, we can conclude that internal energy of a gas does not depend on kind of a gas, but only on its temperature, and also on this amount of substance. Next, we can define that so-called effective or average square speed, so VF, meaning effective or average square speed of gas particle with this formula. So it is square root of this proportion, sum of all squares of gas particles, so gas particle of velocity, not velocity, but speed of gas particle number 1 squared, plus speed of gas particle number 2 squared, plus all the way to the last, to velocity of the last gas particle squared, over total number of gas particles n. There is also average speed, which is different and less than effective speed of the same gas particles, and it is arithmetic mean of speeds of all the gas particles. So this average V bar is smaller than effective speed, and it is, as we've said, arithmetic mean of all. So we sum up all gas particle speeds and divide it by number of gas particles big N. And once more useful thing to say is that from this effective speed or average square speed, we can also, using this one, express average, so this bar meaning average kinetic energy of kinetic energy of a gas, which is mass times velocity. The speed in this case is effective speed over 2. So just like any other kinetic energy, but here we have for speed is this average square speed, or so-called effective speed of gas particles. That's all for today. Now you can take a quiz to test what you've learned in this video. The link you can find in the description of the video. Thanks for watching and stay with us.